so much stuff going on. And I have some show and tell. I'll go through it. So at a glance, look, I do a bunch of stuff with UAVs, so disposable UAVs and self-deploying sensors, advanced multi-rotor aircraft design, robotic aircraft interaction, rotorcraft flexibility, dynamics, and control. Really, I'm a platforms guy. Some people will talk about AI, some people will talk about, autonomy and, long-range navigation. I'm not one of those guys. I work with the nuts and bolts of the aircraft itself, as well as some dynamic controls, algorithms, and embedded flight control stuff. PhD in robotics at ANU many years ago. In fact, I started working on drones in 2001, so I've got about 14 years worth of experience doing this. I would say I'm one of the first generation of UAV engineers. So before I started doing this, the only people who knew what they were doing actually came from the controls community. And so the very early research in drones were from people doing the same sort of stuff as ballistic missile guidance or doing avionics for manned aircraft. After 2001, suddenly we had these new embedded control systems using MEMS technology, and MEMS technology was really the watershed event that allowed us to develop single board flight control systems that they're descendants are with us today. For some seminal papers on UAV design and control, you can hear about the H index of 12, and I have 1,000 career citations. Probably doesn't mean much. I'm an AIC Discovery Early Career Researcher Award. Just delivering messages in a place where you might have jamming. If you want to know that the enemy is on the move and they're jamming the crap out of you, you're not going to get an SMS telling you what's up. Maybe you need a carrier pigeon. Why don't we build artificial carrier pigeons? And so, if we're going to be building disposable UAVs, well, we're going to end up with a bunch of UAVs just discarded everywhere. Why don't we build them out of things that might be biodegradable? Why don't we build them out of things like paper? In fact, paper is a terrific material. You can all probably think of some paper-based aeronautics already. And so what we want to do is we want to find new materials, new processes for building UAVs cheaper, lighter, easier, and have them not poison the environment when we're done. So we're trying to build them out of shredded cardboard, we're trying to build them out of paper, we're trying to build them out of corrugated cardboard structures, and getting complicated molds. We're now using these molds to actually use biopolymers. So biopolymers are actually plastics that are extracted from things like starch or potatoes. Starch comes from potatoes. Or things like cellulose fibers extracted from bamboo stalks and those sorts of things. So the sort of materials you wouldn't normally think would go into cutting-edge aerospace technology, but in fact can be made cheaply and can be made biodegradable. With that in mind, well, now I've got a paper aircraft, how are we going to build the flight control on it? So one of the things we're trying to do is construct flight control systems entirely on a substrate of cellulose or on starch. And these are just some examples of work where we've had substrate. Polyamide is the same stuff they make Kapton tape out of. You guys heard of Kapton tape? AKA God's tape? It's the stuff they just wrapped the lunar lander in. It's terrific. They made it for the space program. We're making paper aeroplanes out of it. Oh well, seems reasonable. So the idea behind this is not that this is a particularly terrific aircraft, but rather to show that you can make complicated 3D objects out of a flat surface, which is already perfect for making circuits on, because that's what it was originally designed for. And so all the flight controllers are built into the same structure as the aircraft itself. We put the voice coil actuators on, and we can show that this will actually keep its wings level and control its angle of descent. This is a terrible aircraft, by the way. We just made it this way so that people could see, flight cheap becomes aeroplane. We're now working on the next generation of this, which will have much better gliding characteristics, and we'll be able to produce them for dollars a piece. In fact, the biggest expense will be the IMU itself doing the flight control, and we'll be able to use them for all sorts of interesting missions. Our long-term objective is to be able to build a $10 UAV that we can put into a hot air balloon or a helium balloon, send up to very high altitude, and then have it glide efficiently. We think that if we can send one up to 30 kilometers using a helium balloon, and then have a glide slope of, say, 40 to 1, which is achievable but difficult, that's 30 times 40 divided by 1, 1,200? What's 1,200 kilometers away from here? How about Sydney? What if we could send a single UAV for $10 from Sydney to Brisbane? That would be amazing. We've also got a whole bunch of other things we can do. We can put bends and folds into the structure of the aircraft to make it stronger. We can put curves in it to get cambered airfoils. A whole bunch of things that we can explore to to try and make very, very capable aircraft out of very, very cheap materials. We're also looking at self-deploying sensors, which is sort of the flip side. Rather than making a whole aircraft out of cheap materials, why don't we build something which is notionally not an aircraft, but give us some capabilities associated with the aircraft. So this happy little fellow, here, is a sensor module. On board it has temperature, pressure, humidity sensors that will be able to give you atmospheric, tropospheric information that might be difficult to get otherwise. A classic example of this would be something like a bushfire. If you could make these for $10 a piece, rather than having a single $100,000 UAV, why don't you simply have 1,000 $100 UAVs? Or if you can make them in sufficient quantities, 10,000 $10 UAVs. And just blanket these across an area, throw them at the back of a larger carrier aircraft, even just as Cessna would do, have them spiral down and soft land all over the place. And then you can have a real-time, up-to-date map of which bits are hot and dry, which bits are cold and damp, which bits are likely to have a bushfire come through, and which bits you don't have to worry about so much. So very different perspective on UAVs. And the trick to this is, of course, the integrated wing is just part of the same circuit board you'd have to fabricate anyway to have a sensor module. Much, much cheaper than having 10,000 parachutes you have to pack by hand to make them soft land. We've done some experiments with CSIRO where we've gotten an off-the-shelf quadrotor and we've put a vending machine on the bottom. You've got the same spiral inside. When it gets to the coordinate, it uses the same function that the software would normally take a picture of a camera. Instead, it activates the vending machine, out pops one of our modules. And they've been incredibly reliable in practice. So yeah, really cheap system, really simple idea, but hey look, we can actually use this to solve real problems. So other stuff that we do is advanced quadrotor design. I've got this one here. It may not look it, but it's actually a quadrotor. It's got 4 rotors, one big one, 4 little ones. And the reason for that is really simple. The smaller the rotor is, the harder it has to work to get the same amount of air flowing through it to provide the same thrust as a larger rotor. With a quadrotor, you've got 4 rotors all the same size, but they're all fairly small. That means you're screaming along very fast, trying to lift the weight of your aircraft. What if instead we could just maximize the size of that rotor by making a big circle that inscribes the vehicle itself, the entire lifting area. So here, 1 big rotor, and the 3 little ones are doing 2 jobs, canted slightly to the side, so they can provide the side force that a tail rotor would normally provide for a conventional helicopter, but they also have the 3 legs of the stool to give us maneuvering control as well. The neat thing about that is that these are much smaller than this one, which means they speed up and slow down very quickly, which means your dynamic control for this type of aircraft can be very, very fast. There is a problem, of course. If you've got 1 big rotor, 3 little ones, nothing's balancing out the gyroscopic forces that'll occur with this 1 big rotor. So what do? If this is perfectly rigid, it'll actually vibrate around and precess, and it's impossible to fly. I know, I've tried, and crashed. I'm not a great pilot. What if instead we simply put a pivot there and let this one do what it wants, and so it can precess around, vibrate all at once, and hey look, the airframe can stay nice and still. And that means when you decouple the motion of the rotor from the aircraft itself, and these things speed up and slow down very quickly, these can keep the structure of the airframe perfectly level, and the rotor just doesn't even see those forces being transmitted. To maneuver, you speed one side up. In fact, coupling between the pitch of the blades and the direction of the mast is what allows you to fly through the air and translate. So we have a patent on this one. We've licensed it to VTOL, a local Brisbane company working in UAVs. And they're building the bigger, scarier brother of that one, which is about that big across. Carries 2 kilos, flies for 40 minutes. And given that every other aircraft they have in that size flies for 20 minutes, it shows you what a massive improvement you can get just by thinking differently about how you design the structure of the aircraft. So aircraft-object interaction, this is something I did back when I did my postdoc at Yale, but we're continuing to work on it, except our photos from here are not nearly as cool. I have some video of this later on if you want to see it. Back in the halcyon days of 2009, the opinion of drone people, and still to an extent today, the opinion is interaction with objects equals bad. There's very few opportunities, short of taking off and landing, where the aircraft is not going to go horribly, horribly wrong every time it touches something. What if it didn't have to be that way? What if we could find a way to make these aircraft be able to touch something and not have a pathological response because of the forces being added to the airframe? Of course, those IMUs inside, which are doing all your dynamic control, are working under the assumption that you're not actually coupled to anything. If they don't know the forces you're putting into it, they don't know how to respond correctly. What if instead we could use some sort of intelligent fabrication approach, some sort of structural design that will allow that to just be buffered a little bit? And so what we've done is we've put in elasticity, what's called compliance, into all the linkages inside our little gripper, so that when we touch an object, we can move and we can be flexible a little bit. And now, when we do the dynamic analysis of the vehicle, we can actually show that we can be stable with certain conditions under the same flight control that we use in free air. Now, that probably doesn't mean anything to you, but think about this. If you're designing a flight controller to work in free air, and it works when you're coupled, you don't need to know if you're coupled or not. The same flight controller will still keep you level and keep you working, even while you're contacting an object. And you don't have to know whether it's occurred or not. So if you come down and you mash your gripper or your probe against the object you're trying to pick up, it doesn't matter. You're still stable. You're still good. And with this, we were able to achieve the world's first outdoor grasp and retrieval of an unstructured object back in 2011. And since this time, the field has just exploded in aero manipulation. It's now a very hot topic in aircraft robotics and robotic research. So if you're interested in this kind of thing, now is the time to get involved. Some boring math. One of the other things we do is, looking at aerial mechanics, dynamics and control, how aircraft stability changes as you move payloads around inside the aircraft, coming up with stability boundary constraints and rotor flapping mechanics applied to multi-rotor vehicles. It's a bit on the arcane, theoretical side of things, but if you're really interested in making an aircraft that will work better than the next guys, this is the sort of stuff you need to do. It's the fundamental mathematical nuts and bolts rather than the physical nuts and bolts that allow these systems to fly. Alrighty, and just to give myself a plug, I really love the rotors that they put on the DJI Inspires, because I recognize them from back in 2008. These are the most efficient rotor blades ever designed for a multi-rotor. They were 77% efficient. The theoretical maximum that can ever be achieved is 81% efficient. And you can get up to 80% in a manned helicopter if you spend a lot of money getting it right. No one else has ever beaten those. This was my 4-kilo baby. This was the AAU X4 Flyer, and I put it up because nowadays we buy a Pixel off the shelf. We use one under here because it's quick and easy. It's got a landing pad. I shouldn't do that with a flight computer. That worked. This was all built, everything by hand. We got solid state IMU components. So way back the very original gyroscopes that you had to solder onto the board by hand, assembled onto a machined aluminium block to keep everything square. Our electronic speed controllers were hand assembled. And in fact, we had braking back then. We had 400 hertz control and kilohertz motor control back before all the cool kids were doing it. We used brushless motors, but they're in-runners, not outrunners, because outrunners didn't exist yet. Back in the day, everything was hard and everything was crap. And we were terrified of it because the rotors wanted a third of the speed of sound. Modern UAVs are so much nicer because you don't have to build all that stuff yourself. But the cool thing is, if you're interested in the technology that goes into these sorts of things, this is the sort of stuff we still do today to try and improve the performance of platforms. We no longer have to do it all ourselves if we buy parts off the shelf. But by choosing where you put your energy into developing a vehicle, you can get much better results than if you just rely on what the hobby guys do. All right. But we do other stuff within the robotics lab. We do stuff for kids with vision impairment, sporting aids. We do planning under uncertainty and mechanics of motion and robot soccer apparently. But I won't talk about that. What I'll do is I'll fire up my other window and we'll have a chat about aircraft design. This is my spreadsheet of doom. I've spent more time looking at this spreadsheet than I think I've spent looking at my spouse. Why do we care? Why do we do the numbers, right? Who here builds their own UAVs? Yeah? Couple? Sheep hands? How well do yours work? Do you get everything out of your design?
Most of the time.
Most of the time. How long does it take to get there?
Depends on generally I follow other people's things. So they spend ages.
So they've spent the time. Excellent. How long did they spend doing it?
A decent amount of time, yeah.
Hours and hours and hours probably. And even then, there's still ways you can tweak it and get it better. If you were to design an aircraft that would fly for 10 minutes and it's cheap to put together, you can just buy a kit today and it's done. If you want to build something that's going to fly for longer, better, and cheaper, and more reliably, you actually need to think through every subsystem, every step of the design. And how you design a drone is actually not a straightforward thing. You're really designing an entire aircraft all at once. And it's not just an entire aircraft. There's no degree you get in entire aircraft design. You need to be a master of aerodynamics, mechanics, electronics, computer design, software development, control theory, broad spectrum of skills. And this is where I like to give a plug to the UQ Mechatronics course, because Mecha plus Tronics, right? Plus robotics. We do all these things here. We also have an aero program, but they're not paying me, so I'm not going to plug that. Okay, so aircraft design. I like to break down aircraft design into a series of budgets. How many budgets can you think of? You get a freebie there because it says mass budget, so that one's for free. What other budgets do you have?
Energy.
Energy, power budget. What else?
Cost.
Cost budget, yeah. What else?
Processing speed.
Processor budget, yes. Can you think of any others?
Communication.
Communication, right, so downlink speed. I don't have processor and downlink speed in this one, and I'm not allowed to show you the budget spreadsheet because that's super commercial sensitive. In the company that I work with, Alaris Inc., we make large first responder UAVs, so fire, police, ambulance. Our aircraft is about the size of a king-size bed. It weighs 25 kilos. It can get anywhere within a city within about 90 seconds. It's a serious piece of hardware. It scares the crap out of me. And we're just about built one, so I'm really looking forward to actually seeing it work. But I know it's going to work. I'm really confident because I've sat down and I've done the math. So I don't have those in this spreadsheet, but this one's got the mass budget and the power budget, which for most of us is what we care about, first and foremost. So where do you start? Where do you begin? Well, what's a UAV supposed to do?
Fly.
Well, yes, okay, good.
Take off.
Take off. At some point, we have to have a bunch of systems that keep us in the air. But we could just build one that keeps us in the air, and for most people, that's fun for shits and giggles. But usually, we want a UAV to do some mission. So we have this idea that we want to carry a payload. Like classic payloads, well, it's cameras. Everybody carries cameras. What else might you carry?
Sensors.
Sensors, yes. So cameras, LiDARs, ultrasonic systems, GPS systems, anything that's not super critical to keeping the aircraft in the air, you can consider as payload. If you have a large enough one, passengers. So because I was having fun with this one today, I decided I would design a flying car. Why a flying car? Because they're aircraft, and also because next week is Money McFly Day. Yeah, right, hoverboards and shit. But I tried using this to design a hoverboard, and I've got bad news. We're not going to have hoverboards anytime soon. But this one is my crazy design for a 510 kilo aircraft, so about half a ton, flying 2 hours, carrying 2 people. Lightweight people, but people nonetheless. So I'll work you through it. Okay. So I start out with a payload estimate. Rule of thumb for a quadrotor is you've got something like a quarter of the mass that you can give over to payload and still fly for a reasonable amount of time. But it's a trade-off. The more mass that you carry, the more power you've got to be putting in, the more batteries you've got to be carrying in order to lift it. And there's this runaway cycle where if you become too ambitious, you want to carry too much, and you don't scale up your vehicle, very soon the entire mass that you've allocated to the vehicle ends up going into batteries. And of course that doesn't work. However, there's a virtuous cycle where if you lowball what you're doing, you design the aircraft too big. Then your payload is smaller, you don't require as much power for that payload, and then so on, you can shrink back down until you reach the point of equilibrium, where the amount of batteries that you need to fly for as long as you want, with the payload you want, exactly matches the mass of the vehicle that you actually build. So I start out with an estimate, total estimate. I could design this to be recursive. That is, I can make all the numbers solve themselves dynamically to optimize the design of my vehicle. I don't do that here, not only because Excel gives me a spreadsheet recursion error, but also because I like to keep my hands on the knobs and levers of UAV design when I'm going through. If I go for an optimum design, if I've missed anything, if I've misparameterized part of the aircraft, I'm going to end up with a result that makes no sense. But why does it make no sense? If I haven't seen the inside of the algorithm that I'm running, then I'm not going to end up with a sensible number. I'm not going to have any insight as to why it's not working. So I start with total estimate based on what my payload is. Here I want to carry 180 kilos of people. Okay, lightweight people, 90 kilos, maybe an 80 kilogram person, 10 kilogram seat and belt and safety buckle, whatever. It could be a converter. We don't have to have a roof or anything. So what's 180 divided by 51? Sorry, 18 divided by 51. That seems about right. That seems ballpark. Maybe a bit on the high end. Okay. Well, now how do I come up with my numbers? Well, where are we flying? Are we flying on Earth? We probably are. So that means there's some parameters that we have to deal with. We have to deal with gravity, which is going to be about 9.81. We're going to worry about air density. If we're flying at sea level, it's going to be about 1.184. It's not 1.184 here in Brisbane. It is in Canberra, which is where I did my PhD. And so that number is seared into my consciousness for all the big calculations I did. But the great thing is, because Canberra is a higher elevation than Brisbane, it means that if it flies in Canberra, it'll fly better in Brisbane. So being pessimistic about your design parameters can help you, get what's called margin. I'll talk about margin in a bit. Then we can stipulate some performance parameters. I've got fuel time. I've got, in fact, 2 hours of fuel time. I've also specified battery time. And that's because my design is for a hybrid electric. Hybrid electric's the new frontier of large-scale UAV development. So who knows what a hybrid electric is? Yes?
Yes, they have a generator which uses some sort of hydrocarbon fuel.
That's right.
Provide electricity for them.
You have an engine that feeds into a generator, that feeds into batteries, and that's what you use to power your motors. Why wouldn't we just run our rotors directly from our engine? Why would we not do this? That seems like a smart thing to do. Yes?
Because stability-wise, you can't then get the nice electronics change in speeds.
Exactly. Dynamic control of the vehicle. If you need to speed up and slow down your rotors rapidly in order to get fast, effective responses, you're actually going to have to be able to slew your power curve, and you can't do that with a throttle engine. In this case, it's also because we want to be able to do that. We want electric control, which is easy to do for things like ESCs, and also because we want redundancy when we're on multiple motors, multiple engines, because you don't want your flying car to fall out of the air and kill all those within, which may include you. So, in this case, we've got a fixed power plant and a fixed generator. I picked some numbers there because I went out of my way to find power plants that were big enough. But there's a whole epic journey to find those motors and those generators that would provide enough power for our aircraft. Other things we're going to need is avionics. We'll have to have rotors, we'll have to have shrouds. Well, we don't have to have shrouds, but I put it in case we want them. A chassis holds everything together, also known as the airframe. But because this is a flying car, I thought it would be cool to call it a chassis instead. We're going to have motors, which are doing our propulsion, ESCs power our motors, batteries that provide a buffer for our electric power system for our engines, power plant generator, the liquid fuel itself, anti-slosh fuel tanks, payload is the people who are sticking in it, and this thing called margin. So margin is fun. I like margin. Margin is that thing where you simply say, gee whiz, I don't know, I've probably got this wrong. Which is to say, anything that you ever design as an engineer is going to be worse than you thought it would be. You'll optimize the crap out of your design, you'll do all the math, you'll get all of the parameters perfectly right on your spreadsheet or in MATLAB, and when you go to build it, everything will weigh like 5% more. How do you get around that? Well, as engineers, we actually become professionally pessimistic. Whenever I tell my students, we're doing the experiment today, yeah, it's not going to work. And the terrific thing about having that attitude of it's not going to work is that sometimes you're wrong. And when you're wrong, you're too excited because it worked, and so you don't care that you were wrong. Most of the time you'll be right, and everyone will say, yep, Paul was right again. So please be pessimistic, especially in your engineering design. And this is where factors of safety come into it as well. When you design a system, you put in a factor of safety, you're building in margin. So here, my margin is actually incredibly small because this is pushing technology right to the limits to build something crazy from a film in the 1980s. Our margin is actually 2.5%. Depending on the system that you build, your margin may be 5%, or if it's a normal engineering system, it might be 10%. For things which are safety critical, like life support systems, your margin might actually be 300%. And that you need to have 300% factor of safety 3 times what you think you would need just to make sure that it will never, ever, ever fail. And a good example of that would be things like triple redundancy. So coming back to my startup company, our flight control system is actually a triple redundant system so that we can lose 2 flight computers and still keep going. We've done the math and we've found that if we lose a single rotor, we can continue our mission. If we lose 2 non-contiguous rotors, we can continue to safely land. If we lose 3, then we're shit out of luck. All right. What we want is all these things that we estimate that we need to add up to less than our total. That makes sense? Total sum of the parts of the vehicle should weigh less than the whole vehicle itself. Anything that we have left over is called deficit. So here, I'll put in bold, minus 0.099 deficit. What that means is that there's unaccounted for in all of this stuff about 100 grams worth of material in a 510 kilo aircraft. So if we can't find something to put that deficit towards, we'll just add it to margin, because margin doesn't weigh anything. We just assume that we'll consume it. If that aircraft ends up being slightly underweight than what we designed, hey, that's cool. We can put more fuel in. What you don't want is you don't want this to be a positive value. If that's a positive value, it means you've got to put more stuff into the aircraft to make an aircraft of a certain mass fly than you have mass. And that's just not going to work. So a good question is, where do these numbers come from? Some of these you know, some of them you specify. The weight of the payload, I'm just saying, yep, 2 people, 90 kilos each, that's it. It's stipulated. Other things like power plants, you go out and you look at how much you need, how much you think you're going to have to put up with, and you size that piece of equipment to fit it. Other things like fuel, you can compute. You see it doesn't have a nice round number there. That's actually computed from the total amount of power required per second times the total number of seconds we need to fly, times the total amount of power that we need in order to fly. And so it ends up with this complicated number that we can then enter into our spreadsheet. We can compute all of these things analytically. Likewise with batteries, likewise with ESCs. It seems odd that we wouldn't just pick an off-the-shelf ESC. But when you go up to an aircraft of this size, the ESCs that you get, you're no longer really constrained by what's available on the market because you need to build them yourself anyway. Yes, you can go out and you can buy industrial ESCs that will spin a 90 kilowatt power system, except they're going to be industrial and they're going to be huge. You're actually going to have to re-engineer something that will solve that problem. If you can't buy it off the shelf, you're doomed to do it yourself. Things like chassis, here I've calculated my chassis weight by simply saying, I'm going to take 13% of the total mass of my vehicle, that's going to be my airframe. Where does that surprisingly specific number, 13%, come from? Any guesses? No? Well, 2 places. I sort of call them the same thing. One is trial and error. That is to say, you've tried building 100 airframes, and the ones that worked were about 13% or more, and the ones that didn't were less than that. And the other one is experience, which is the polite way of calling trial and error. Or better yet, you've gone out and done some research on other people's experience, trial and error, until you found it first. In this case, I can tell you 13% for the airframe is probably a bit pessimistic. We can probably do better than that. All right. Rotors again, we have a parameterized number for that, and avionics, I've said, oh, yeah, we'll hot dog it, we'll get something off the shelf that'll be about half a kilo. Okay, great. All right, well, how do we know what kind of power we need? How do we know how big our power plant's going to be? This is where we have to go back and do a bunch of math. Fortunately, this is the bottom of the spreadsheet. So here we have our drive units. You may have noticed before, I actually specified this is going to be a 6-rotor flying car. Why 6 rotors instead of 4? Well, 6 rotors sounded cool. So for each drive unit, we've got to carry about 1/6 the weight of the total aircraft. We know how heavy the aircraft is, so we know how much power we need. We know how much force we need, so we can calculate the total thrust and the total thrust per rotor. Then we end up with this parameter of rotor radius. Rotor radius is how wide your rotor is going to be, and at 1.3 meters, radius, that's the whole thing's going to be whopping big. It's going to be massive, massive aircraft, which is not as flying car as we would like. But if we change that parameter, we find that our power goes up. So the amount of rotor area that we have versus the amount of mass we need to carry on it is what's called disk loading. And if we design our disk loading to be high, we're going to require more power than if it's low. What do you think is a conventional aircraft with this loading? Any ideas? No? For something like a Robinson, they'll be about 44 kilos per square meter. For something like a heavy UAV, it'll come down to about 20 kilos per square meter. If we come down to a really, really small aircraft, these ones might be as low as 6, perhaps, depending on how they're designed. That great big 4 kilo small rotor, the one that I showed you from my PhD, had a disk loading of 12. That one's actually pretty pessimistic, simply because its rotors are really weird and really strange. But they're also very, very efficient. So I've designed this one to have a disk loading of about the same. That's, again, probably quite pessimistic, but I'm treating the rotors as being especially small and especially crappy. Okay? So from that, we know how much weight we have to carry. We know what we want our disk loading to be, so that tells us analytically how big our disk is going to be. And from that, we can calculate its disk area, and from that, we can calculate the disk loading. I designed 15. In fact, what's popped out of the calculation is 14.997. So that's just Excel rounding numbers. I've got this thing called thrust margin. What's thrust margin? You don't know?
Stability. So basically, well, you need to be able to lift 30% extra beyond the weight, and part of that is if you have a gust or something like that, you need to be able to have the authority to correct it.
That's right. Because if your aircraft can only deliver exactly as much power as what's required to hover, well, if you want this side to go up to turn, you can't lift it. In fact, you'll never get off the ground in the first place because you simply don't have enough extra force to give you vertical acceleration. So for a conventional helicopter, that's about 1.5, that thrust margin, so that is they can develop about half as much power, half as much thrust again as needed to hover in order to be able to maneuver. For a drone, 1.3 is normal, 1 is totally right out, and crazy acrobatics helicopters can be all the way up to something like 3. That is, they can develop 2 G's vertical acceleration, and they look like a rocket when they go. Those guys doing crazy TikTok maneuvers with their hobby helis, yeah, those guys have acrobatic helis that will pull a thrust margin of 3. That tells us something important. That means we're no longer just calculating what our system can do in hover, which is where we would normally think we want to fly. We actually need to spec our vehicle to be able to produce more than that. So if we design an engine and a power plant and a rotor that can pull 1 G, terrific, until we need to pull more. So we actually need to specify our entire drive system to be able to provide us upwards of 30% extra. And if we design our engine to be only for the hover condition, we're simply not going to have the power we need. So that gives us 2 measurements for doing our power analysis. One is continuous power per rotor, and one is peak power per rotor. Peak power is when you're pulling that full extra 30%. Continuous power is when you're just pulling 1. So that gives us a couple of parameters. Induced power is the power dynamics tested. From that, we can have what's called induced overhead. What's induced overhead? Well, that's the ideal induced power. In fact, it's always slightly more crap than that because your disk is not infinitely size. It's going to have tip loss. It's going to have an internal hub loss because you'll not be developing lift all the way to the center of the rotor axis. So you're going to end up actually being slightly crappier than you think by about 10%, good rule of thumb. So your actual induced overhead, that is the amount of power required to generate at the rotor to produce the amount of power in the air to keep you in the air, is higher than you thought. Shroud effect, if you have rotor shrouds that give you some sort of lift advantage, you can calculate that here. I'll just put it to 0. And shaft power is the amount of power that you need at the rotor itself, driving the rotor itself in order to get the induced power. Because rotors are actually really crap. I said before that we had a 77% efficient rotor. That means of the power going into its shaft, about 3/4 of it, slightly more than 3/4 of it, actually made the air move. And then we had tip loss on top of that. So we're going to require even more power than what the ideal aerodynamics says we should. And once we've gone from shaft power to electrical power, we have losses in our motor, losses in our generator, losses in our engine, all which take away from our ability to put energy into the air. Oh, okay, that's great. So we end up putting 6.5 kilowatts of power in the air per rotor. It requires about 11 kilowatts of power to actually do that. And of course, at peak power, we require about 30% on top of that. We're going to have about 16 kilowatts of power. So if we do all the math, we sum all of that up, here's our total craft power. For all the engines that we have to provide peak power, we're going to have something like 160 brake horsepower to drive our whole aircraft. That may not seem like a lot, it may not seem like any particular number, but when our power plant is only expected to be 42.8 kilos, that's actually tremendous. We've had to go out and find really crazy high efficiency, high power density power systems to be able to get that kind of induced power. And that's why we don't have flying cars. But this one would work. I found parts that will make that work. So I talked about peak overhead as being 10% just thrown away. This is where these numbers come in. Our aerodynamic losses, we're using 70% efficient rotors. Our motor's 88% efficient, our generator's 88% efficient. If we had special shrouds that would allow us to shape the flow through our rotors to be more efficient, we would compute that there. Then we have specific fuel consumption, specific weights. If we were analytically computing how big our motor has to be to provide the amount of power throughput that we want, we can actually put these numbers in and compute systematically how big each component of the aircraft has to be. In fact, there's a whole bunch of rule of thumb numbers for this, some of which I'm allowed to give you, some of which I'm not, that you can use to spec any scale aircraft that you want, all the way from a very small aircraft up to a full-size passenger aircraft, and parametrically design your drone or aircraft. And this spreadsheet is just a subsystem of all the rest of the spreadsheets that feed into it. Computing things like your specific mass of rotors, I've rounded it to 2.5. There's actually a ton of work that goes into computing what the systematic, parameterized weight of a rotor will be, because it depends on the quality of your manufacturing, it depends on the materials available to you, it depends upon how efficiently you can design the structure of your rotor. So if you can get away with less rotor per unit area with the same aerodynamic efficiency, that's a distinct advantage that other people in the aerospace industry don't have. So this number is actually pretty sensitive, and we don't give that one out. Likewise, chassis I've rounded off a bit, and petrol, you can look that up from Wikipedia, I know I did. Okay, things like battery. This is an interesting one. I spec here 1.75676 times 10 to the negative 6 kilograms per joule. Most people who specify battery packs for a drone will tell you it's milliamp hours. Well, it's a milliamp hour. The number of milliamps for an hour. Okay, but they don't tell you what its voltage is in that number. In fact, when you multiply seconds per voltage per amp, you get out joules. And so the thing you really care about is joules per kilo, or in this case, it's parametric inverse, kilograms per joule. If you know how many joules you need for your mission, you can calculate how many kilos of cells you're actually going to need. And the cool thing is, people publish this number. You can go out and you can find watt hours per kilo or kilos per watt hour from various manufacturers like CoCam, because they're used to dealing with people who build things like the F-35, where you need to know these numbers in a parametric form, so you can just plug them into your spreadsheet and design your aircraft. The best I've ever seen are 262 watt hours per kilo, which is unreal. And I was blown away when I saw these cells, because these ones which I have specced for this are using, I think they're 178, and the average ones that you would get would be around 150. 262, what's the catch? Turns out you can only charge them 60 times. What would you use those for? Remember, we're talking about disposable UAVs. You put them in your cruising split, it goes bang. So you don't have to recharge them very often. Right. Okay, so, hey look, where have we started from? We started from specific parameters to characterize our aircraft. We've started from fundamental laws of physics stuff like gravity and the number of rotors. And from that we can compute analytically all the subsystems, and we show that we get out a total that's less than our actual requirement. We've calculated the amount of power required to be produced for each of these things, and if we size our power plant to be greater than that number, we know we're going to be able to provide enough watts constantly or peak as required. So a whole bunch of numbers. What does this mean? It means if we go out and build this aircraft, we actually have a chance in hell of making it fly. Now for a little quad like this, I mean this is one we built in our lab, we dinged around with it until it worked. It's made out of a single circuit board and some twigs. If we got it wrong, maybe we'd blow $200. The aircraft that this spreadsheet was originally designed to build, the starting price is $250,000 for one unit, and that's not including the mold as well. If we get it wrong, it's the end of our company, right? It might even be the end of our solvency if we mortgaged our house to start the company. I haven't done that, others may have. So it's really important for us as engineers to actually get this stuff right. And the way you get it right the first time is you do the math and you get very paranoid about what your margin will be. In this case, I've cut all sorts of corners because I didn't have a lot of time to get it for you. The full spreadsheet is pages and pages and pages of detailed calculations. All of them we then translate to a CAD model, and we actually know what the variance that we can tolerate in each of our components is, not just in terms of mechanical fit, but in terms of mass fit. We actually have a mass budget sensitivity analysis, which allows us to know that if our ducts are 2% thicker than they should be, we're boned, right? So when we go to a manufacturer, we can say, you've got to give us this tolerance, and if you don't, we'll sue you. So this are serious business when it comes to designing UAVs for real professionally. And this was a learning curve for us because I'm an academic, I'm a researcher. I build funny little things that you throw out the back of a vending machine. If you go to work for someone like Lockheed Martin, if you go to work for someone like Boeing, they'll actually expect you to step your game up enough to be able to give them parameterized estimates of all of the forces on every part of your aircraft. And just like CASA approvals and how you show that your aircraft's not going to fall out of the sky by knowing the bolt shear stress in every part, you'll actually need to show what the vibrational mode analysis on every surface of every composite part is going to be, because otherwise you may have a failure mode that you didn't anticipate. And you could say, oh, just make it twice as thick. Nah, you don't got that much margin. So every part of the aircraft boils down fundamentally to how paranoid you can be and how good your technology is in setting these numbers and setting these numbers. And that's why they're so closely guarded in the aerospace industry. So yeah, anyway, that's the other side of the coin. So I probably bored you all to tears, but I'm happy to take any questions you've got about this or about research stuff or just UQRobotics in general. Thanks.
What kind of material advances would be most useful for improving UAVs or light aerial vehicle design? Is it obviously already using, carbon fiber parts and there's lighter, more energy dense batteries and so on, but what else is?
There's three things. The obvious one is, of course, LiPo cells. Get us better batteries, get us pocket fusion reactors like Back to the Future, and this will be doable, right? There's mechanical structures, so removing parasitic weight. And parasitic weight is anything that doesn't keep the aircraft in the air. That includes things like fuselage. Fuselage doesn't make it fly, it just keeps the flying bits together. Things like anti-slosh fuel tanks, they don't make it fly, they just keep the fuel that makes it fly from spilling out everywhere. If you can thin down those margins increasingly accurately without it failing, you'll have a strategic advantage in designing a better aircraft. But the one that people forget is actually the electrodynamics of Lorentz force actuators is still very much a black art. Tesla was such a god because he could see all of the field windings in his head and just make something that worked. Today, we're not interested in just making it work. We actually need things to be super efficient. One of the fascinating problems with it is that as you push these motors harder and harder, what happens to them? They don't stop working, they just get hot. And they get hot because of parasitics inside the motor design itself. If you can break down all of the eddy currents, all of the back EMF effects, all of the places where power is being diverted from motive power into thermal power, you'll actually be able to get something like 10, 20, 15, 50% more energy depending on how your system is set up than if you had designed it in a slipshod way. So electrodynamic performance, better conductors, just wiring. Weirdly enough, for my 25 kilo first responder UAV, something like 600 grams is just wire, just bits of copper, and you wouldn't imagine it would weigh nearly that much. But holy shit, that's a ton of weight. How do you solve that? Well, for us, we said, okay, wire is to go from batteries to speed controller to motor. And you put them as close together as you possibly can, you cut out that parasitic mass. So designing your aircraft to get around your materials limitations can be a really effective way of actually improving the performance. And you can tell when someone has loved an engineering project. You can tell when the designers just were besotted with their project because they'll have gone through and they'll taken out all those little sub-efficiencies, all those imperfections, and they'll have fused it together to be elegant and really functional. Other questions? You were first.
Where does the 83% maximum efficiency for motors come from?
For motors, motors can be much more efficient than 83%.
Oh, the propellers, sorry, not motors.
Oh, the 81% efficiency.
Yeah.
It ends up being something over a square root inside a square root.
Right.
Basically, it boils down to the fact that as you start to put more energy into the air, you get more parasitics than what you get out. It's a fundamental property of
So is
physics.
that specific to our atmosphere?
It's specific to atmosphere,
Just in general.
to physics, right? So gas fluid dynamics. Even if you could exactly solve Navier-Stokes equations analytically, you could not get any more out. It's kind of like how when you have an impedance match in electric circuit, you can only get out sort of half as much as you put in, and if you do anything worse than that, you get out less.
Yeah.
But you can't ever get more out than half. It's just, physics works that way, unfortunately. So being able to get that extra couple of percent is normally not worth it for people, unless they're crazy and just love it to pieces and say, no, 70% is not good enough. To give you a sense of scale, though, most of the props that you use will be something like 60%. I don't think any of us are...
These are probably the most efficient propellers you've ever seen.
Yeah, maybe. So these are really small. So the smaller you are, the less critical your geometry is, because everything starts to look like a flat plate. When you're in low Reynolds numbers flow, this will be probably around maybe 70,000 to 80,000, depending on how fast it spins. A flat sheet is actually a really good approximation for a good airflow. As you get up to something like, say, high-speed jet flows, then millions and millions of Reynolds numbers, it really actually matters to get your profiles right, because the air is then dominated by inertial effects rather than viscous effects. So part of the reason why I have a hard on these ones quite so much, aside from being based on my PhD research, is that the airfoils in here are very, very specially designed. When I designed my ones, I want to bring up a picture of it. So, goes at a third the speed of sound. So very fast, because this cord tip is so narrow, it's 12 millimeters across. To get efficient aerodynamic flows, we've got to be screaming the air across it to make it behave like it's a much larger aerodynamic structure. That's great, that lets us get a lot of lift out of it. But in fact, what's really bizarre is because we're getting a lot of lift out of such a thin profile, I mean, these things are probably less than a millimeter thick through most of it. At the tip of ours, they were 0.2 of a millimeter thick, and it's like getting down to paper thin. And we were lifting 4 kilos of robot on it. So what would happen is, as we were loading the leading edge of these airfoils, it would actually twist, and the whole thing would twist until it stalled. So to fix that, we designed a very special profile with this sort of snub-nosed, thick-bodied, but very long and high aspect ratio airfoil. And what that would do is a couple of things. By being thick-bodied, it would stop it from having just a flat, twisting surface like this one. Here I can just twist it like that. If I add more mass further away from the center axis of that, it becomes harder to twist. By rounding the nose, it actually makes it less susceptible to stall. With a sharp leading edge like that, the moment you have any sort of deflection, the flow will just separate and go off, and you won't get any lift on the stall. Combining those features together whilst keeping a fairly slender profile means that you can make it resistant to forces causing it to go off axis, but it doesn't solve the problem. What we did is we actually designed it through an iterative aerodynamic aeroelastic simulator. We would set the angle of attack lower, so the inboard part of the rotor would start to twist up, which would cause the next part to twist up, and finally the tip to twist up into the most efficient angle of attack of those blades. So under hover thrust, they become very efficient, because all of those elastic distortions are accounted for in the static resting design. And we did a whole bunch of analysis to get the carbon fiber material perfectly tuned, so that everything twisted in the right way. It's actually a feedback control loop. If you spin faster than the design hover speed, it twists harder, and so you get more drag, and it causes it to slow down. If you spin slower, it'll not come up to the right angle of attack, it'll produce less drag, it'll actually speed up. And so we can move around this very accurate hover velocity that we've designed into the structure of the rotor itself in order to make it super efficient. And it's bizarre because this aircraft was designed with 50 hertz gross control loop, 400 hertz motor control loop. We didn't need the motor control loop at all. In fact, the structural design of the rotors did it for us. And because we had such crappy control, it still worked really well because the rotors were just governors. And so as they moved up and down within their own flow, they would dynamically interact with changing flow conditions through the rotor to provide passive damping. And so this helicopter actually flies better than pretty much any other aircraft in its era, simply because the passive structure of the aircraft is one that leads it to be more stable. The best competitor that we had, I think, similar performance to us, but they had a gigahertz core running through an FPGA, driving little rotors very fast. And they were able to get half a degree plus minus. We were half a degree plus minus on a 50 hertz controller. And that's just the difference of thinking carefully about the structure of your rotor makes when it comes to designing an aircraft. So yeah, I really like these ones. They have the hyperbolic twist and hyperbolic chord profiles. When you have a rotor, out at the tip, you're going to be spinning a lot faster than in close to the hub, simply because you have more of a subtended swing. That means that this part's going to be seeing faster air than this part. Well, you get around that by making this one thicker and this one thinner so that your Reynolds numbers are the same. If you don't do that, you get cross flow across the rotor, and cross flow means you're going to have pressure leakage. And that pressure leakage means you're not going to be developing as much lift relative to the amount of power that you're putting in. And when you see the vortices and eddies coming off the tip of a rotor or a wing, that's actually parasitic leakage of lift causing these turning, spiraling corkscrews of air. And that's why commercial jetliners put winglets on their wings, so that they can actually extract the energy from those spiraling vortices of air. Because if you're accelerating air in a circle, you're not accelerating air down. Air going down is what makes you go up. Air going in a corkscrew is just wasted fuel. So airliners use winglets in order to improve their cruise economy, not because it provides more lift or anything like that. It actually provides propulsive force. Yeah. So, sorry, that was me talking about rotors because I'm crazy about rotors and rotor design. Yes, you know.
Just quickly, were they fluttering just only plus or minus half a degree?
Sorry, the rotors?
Yeah, were they fluttering or
Not
was it
even,
just
not
steady?
even close. They were very, very steady. If they fluttered, you'd actually, plus or minus a degree is huge. The total angle of attack is 4.4 degrees in an optimal design. So that kind of flutter of 1 degree would make the whole aircraft shudder. We estimate it would be something of sub-degree aeroelasticity. But what's interesting about aeroelasticity is that aeroelasticity is this dynamic balance between the aerodynamic mechanics, the elastic mechanics, and the momentum mechanics. Because our rotors weighed so little, the momentum mechanics just disappeared. And so you had elastic and aerodynamic mechanics, and the aerodynamic mechanics are very fast, the elastic mechanics are very fast. So what would happen is that the vibrations we would get would become very small, high-frequency and dosing. That said, we still put lots and lots of vibration damping on all parts of the aircraft. Out here on the motor carriages, they're isolated by little rubber grommets you can't really see. And internally, this is actually suspended on a tetrahedron of rubber isolations, because you couldn't just buy this rubbery, gummy, vibe tape stuff you can get now. Nobody had the little 8-ball suspension things. It didn't exist. So we made it out of baling wire and glue. In fact, the vibration system we used was originally for turbo machinery, because it was all we could get that was tuned to the right vibration frequency for our system. But yeah, very small perturbations. In fact, I just realized the pizza was here, so I'll get out of the way.